Okay, let's start. Just before beginning, we welcome Sarah in the team of the UIB-CSIC, with binary function. And whenever she's alone, or one of us is alone, invited to help her, for the beers and everything, you know the deal. Okay, so today we have Máximo with us, and Máximo is also part of the modeling team from the subsea. So you may never see them because they're the first floor on the right there, below. But thank you very much.
Good afternoon. Thank you for the invitation. I'm coming to the media seminar. In the framework of the CALYPSO work, I will present the analysis of vertical velocity associated with the meso and submesoscale in the Alboran Sea and the Balearic Sea in the Western Alboran. This work is done by the glider and modeling facility at the SOPI and in collaboration with the colleague on CALYPSO. Okay. So I will present the outline. In the beginning, I will present the goal and the CALYPSO project and for background, then the results from the Alboran Sea and the results in the Balearic Sea, and then the conclusion. So, CALYPSO is the acronym from Coherent Lagrangian Pathways from the surface to the interior. It's funded by Horner Department Research Initiative in US and is leading with by Amala and Eric Dasaro from Bursol and in Washington University, respectively. This cartoon is an example of a sea experiment in CALYPSO. In general, we use two research vessels and the SOPI catamaran to deploy several multi-platform observations, and we use satellite image and forecast model for the support. The main collaboration is Pierre Lomino from MCT in the Massachusetts Technology Institute, the glider team from Nescript, with tank running, and the immediate colleagues. So the goal of CALYPSO is that CALYPSO address the challenges to observing, understanding, and predicting the 3D pathway from the surface to the deep level. This is an example of a subduction area. The parcel is subducted associated a this satellite image show also a structure that can generate large vertical velocity. So CALYPSO is a spatial temporal problem scale. The ocean is a turbulent fluid in which motion awaits large scale from 1,000 kilometers to centimeters. And this structure can interact and exchange energy. In the spectral in the wave spectral plot, you see the large structure as the sharp gyre, the subtropical gyre, the thermal in circulation, the mesoscale eddies as the Alboran gyre for the current eddy is around 200 kilometer radius, and then the small scale filament small cyclone about 10 kilometers. And these structures can interact, exchange and cascade energy between them. The Rorty number is a quantification of the activity. For example, for 2,000 meter model resolution, we would have the mesoscale sub or mesoscale activity, and 350 meter model we have the submesoscale activity. In CALYPSO, we try to measure the vertical velocity are weak, and in CALYPSO we try to observe it, and it's difficult. But the meso and submesoscale are efficient transmitter of heat, transfer, biogeochemical transfer, plastic from the surface to the different layer. Because this structure showing satellite image, this is the Western Alboran gyre, and this is the Almeria front, can develop large vertical velocity. So a little bit the background. The mesoscale is defined by a scale, a spatial scale from 100 kilometers to 10 kilometers and longer than which. And there are associated a small Crosby number. So this is a non-divergent flow in 2 dimensions. In other hand, the submesoscale is defined by a spatial scale between 10 kilometers to 100 meters and lasting between hours to days. So they have associated a Crosby number close to 1, and they become strongly divergent. So we have a 3D flow. So for the other hand, the mesoscale are associated a small vertical velocity, about 110 meters per day. In 1991, they measured in the Alboran Sea vertical velocity about 20 or 30 meters per day. A recent companion paper from Zanacalenos and me in 2020 will report similar velocity from glider and model data. In the vertical velocity associated as a mesoscale structure are larger and is around 10 meters per day. And Danny Tarry from Melia from Richter cluster measured 100 meters per day. The result. So this is the Alboran Sea circulation, is dominated by 2 quasi-anticyclonic gyres called Western Alboran and Eastern Alboran, and the Almeria front. What is a front? A front is defined as a structure that separates light and water and dense water. For example, this is the Alboran Sea. We have the relative light water from the Atlantic and are separated by a front, the relative dense water from the Mediterranean. And then the structure of a front is a long jet associated with the Atlantic jet, and we have a cross circulation in the spectrum. This is the cross circulation. We have a downwelling in the dense side and upwelling in the light side. This is the definition. So this slide shows the CALYPSO experiment in 2018 and 2019 and the deployment of different instruments. This study is focused in the first CALYPSO Sea experiment in 2018. In the modeling facility at Sochi, we developed the DULOMOD, is the model Western Mediterranean Operational Ocean Circulation Model. It is based in a regional configuration of fronts with a 2 kilometers is from Gibraltar to Sardinia Channel, Gibraltar Channel. It's a 2 kilometer resolution grid with 32 vertical levels. Then every day we run a real-time and prediction forecast. And this forecast is used during the planification and during the experiment. This forecast assimilated data, satellite data, and R. And then we produce 2 other products called the reanalysis. In the reanalysis is we did a simulation product with CALYPSO data. In this movie, we show the data from CALYPSO are assimilated last year. And then we have the hindcast. The hindcast is sometimes we configure a reference grid to understand and analyze the ocean process and the variability. This is a fine grid by 400 meters. This is the Alboran, the Almería Alboran. So this is the data technique that I used in 2018. So we start with satellite program by image. This is the intensification of the Western Alboran front in the middle of June. And then in July, in the beginning of July, we have the intensification of the Eastern Alboran. Also, we use the glider. The glider monitor the Eastern Alboran front, the line, and the glider show the separation between light and dense water in the Mediterranean. And then also we use CTD from the Curcuapa vessel to study the Western Alboran. So this slide shows the comparison between CALYPSO data and double mode model. This plot is the vertical profile in the Western Alboran front from the CTD and the model. We reproduce well the slope and the dense and light side of the front. On the other hand, this is the Eastern Alboran front from the glider. The glider is the dot, and this is a Muller from the model in the background. So the model don't reproduce well the variability of the front. In the vertical profiles, we see also the model is a little bit offset about 20 kilometers, but we represent well the isopygnal, the pointing isopygnal, and the bell-shaped isopygnal. So we can say the double mode reproduce well the process behind the intensification of the Western and Eastern front. So this is a Muller diagram about from the vertical velocity in the Western Alboran front and in the Eastern Alboran sea. In the black line is the section. So they present the evolution, the temporal evolution of the vertical velocity. So the red box represents the intensification of the front. This is the down subduction area, and the Western Alboran front is stronger, deeper, and long timing than the Eastern Alboran front is weaker. So the question here, the motivation from why are the vertical velocity developing different between Western and Eastern Alboran front? So for that, the top panel shows the intensification of Western Alboran front. So this is the Western Alboran front. This is the vertical profile in the Western Alboran front, and the Western Alboran front intensification is done by frontogenesis mechanics. So we have intense buoyancy gradient, and then a large spin rate and cyclone vorticity in the dense side, and that produces a single anisotropic circulation. This is the across circulation between across the front. In the dense side we have the subduction, and in the right side we have the upwelling side. On the other hand, the Eastern Alboran front is intensified by a philantogenesis. It's intensified by a core filament that is directed to the interior in the Mediterranean Sea. This is a satellite temperature image, and this is a cross-front section from a glider. This is the core meanders. And this is the diagnostic for the philantogenesis in the Eastern Alboran front, and they produce a complex vertical velocity structure. So we have a downwelling in the middle of the filament, and in the border of the front we have two anisotropic secondary circulation. Now we present the result from the preliminary result from the Balearic Sea campaign. So the CALYPSO Balearic Sea campaign is focused in the submesoscale, where the isotrophic balance breakdown and the isotrophic flow can create the circulation across the gradient or across the flow, across the fronts. So this is the circulation in the Gulf of Lagrange and in Balearic Sea. And this satellite, these temperature satellite image show the structure observed during the sea experiment. We have the frontal area, and they develop very small cyclonic eddies in different places. So in CALYPSO experiment, we deploy a multi-platform observation from glider, float, UCTT, from in the middle of February to the middle to the March 2022. So this slide also shows a comparison between the CALYPSO data and the dual mode model. This is the satellite temperature image and the UCTT from the CALYPSO experiment. So they represent the observation show a Mesoscale warm vortex dipole associated with the main front in Balearic Sea, and the model reproduce more or less the frontal region and the gradient between temperature. But for this study, to study the submesoscale, we developed also a new high resolution grid. So it's called subduction. It's 650 meter horizontal resolution, and it's the boundary condition comes from the remote. Here we show the mesoscale activity in the 2000 meter simulation, and in this map we show the mesoscale activity in the 650 meter resolution. So from the 2000 meter simulation, we studied the evolution of the Balearic Sea plant. In this moment, we show the diagnostic from frontogenesis in the from Balearic Sea plant. So the intensification of the Balearic Sea plant is due from frontogenesis mechanism, and during this event, we have a strong wind event that can trigger the condition for overturning stability in the mixed layer that indicate the start of collapsing of the plant. Sorry. The blue region is the condition for the instability. So we need to think it's about the sloping the isopygnal. So this isopygnal in the movement is transferred mean energy to the turbulent flow, and they can create a smaller structure. Then the wavelength spatial spectrum show the horizontal kinetic energy and the vertical kinetic energy for the 2000 meter simulation and the 650 meter simulation. The 2000 simulation don't sufficiently develop the small scale because we have effective resolution about 10 kilometers and the new grid about 650 meters develop solve the submesoscale activity. Then this is the horizontal, this is the vertical kinetic energy. So the velocity has more energy at depth, and particularly in the small scale, in the submesoscale domain, become more intense. So this is in agreement with the theory. Also, for the identification the 3D pathway from the frontal region, we see 1,000 particles in the Alboran, in the Balearic Sea. at the 10-meter depth, and we advected with the 3D velocity from the 2000-meter simulation and 615 simulation during 3 days. So the particle is distributed around the meso and submesoscale structure, and then in the vertical they have asymmetrical final distribution. This shows the number is the final position of the particle after 3 days integration. So the 650 meters show a decrease of number of particles near the surface and indicate a larger number of particles reached to the depth. For example, we have 70, 150 particles deeper than 60 meters. In the core simulation, we have only 20 particles in deeper than 70 meters. So the submesoscale structure enhances the vorticity, the divergence, the stress rate, resulting in more intense subduction area. Also, in the CALYPSO, we are trying to observe it. This is the main from Balearic Sea. We observe a meso-rich structure and generate a submesoscale cyclone eddies, and they evaluated in the Balearic Sea. This figure is the surface temperature from satellite. And then now the work in progress, we are creating from the reanalysis using all data set from 2022, assimilating all UCTV, flow radar, satellite, created the more realistic initial condition to solve the meso-ridge is more or less in this position. This is the sea surface temperature. This is the sea surface temperature with CALYPSO, and we are working to localize the generation of a small eddy cyclone eddy in the ridge. For the conclusion, so the 2018 analysis of process of vertical velocities through high simulation and glider observation are reported in companion papers from Tanacalenos and García-Jove 2022. So, for one hand, we have the Western Alboran yield front and the Balearic front are intensified by the frontogenesis mechanism. The Western Alboran yield front is deeper, longer, and producing more subduction area. And on the other hand, the Eastern Alboran yield front is intensified by lantogenesis. There are a cold meander that is affected to the interior of the Mediterranean Sea, creating a weaker frontogenesis, but they develop two isotropic secondary cells across them. This is the formal conclusion, and there are summarized in the previous.
In the model, they use waves and the storm drifts to drift safety to waves.
No, we use only the wind. I did some work with the partner is a Ocean Partner program, and we with Alex, we did some experiment with the wind drift and the top drift could be pattern, wind, no wind, but in the surface of the model to feel the wind.
Because you talk more on vertical facilities, currents, but you said, for instance, in the work of García-Jove, with drifters, with Lagrangians, you have the vertical currents. So you never take into account the way, because if you don't have a strong structure, I guess maybe the subgrid could be significant.
Yes, the problem we come is the problem is the spatial temporal. So these features are 7 days, 5 days light, so they don't feel the big stroke wind, but I don't present it there, right? But there are other effects that can amplify it. This is all these mechanisms are mechanisms that can enhance the vertical velocity. So I don't speak, but we have the non-linear effect, and it's linked with the wind, but it's more to the wind affecting dense water to the light side, and they create across the circulation. So in sense, but it's more in this sense. The difference, I think, is too small to feel the front or perturb the front. But at the same time, the wind affect to target the stability. So it's another step. More than one day, 1 week. It depends on the measures.
It's a very secret question. I thought the upwelling that happened in the Morocco coast, like the Canary, like near to the Canary, was due to the when the currents interact with the continent, and it produced that weather. And how the coast or the outline of the coast is affecting this model.
Yeah, no. This is another process, but it's very close because you need to think the front is like a physical border.
Okay.
So it's linked with the Ekman. The welling in the this kind of welling you put in the western boundary. So you need to have the current and the wind. 90%, the wind, the good direction, and they create the perpendicular transport, they generate the welling. But this is another topic. Okay. But it's very similar, because the front is like a physical border, because the fluid, the dense and the light side, they don't want to be. If you put the water together, they start the instability and you start the collapsing of the front. Then
Nikos,
Yes.
¿tenías una pregunta?
Yeah. Sí. Tiene una pregunta. Thanks, Danny. Máximo, just a quick question. do you have an estimate how well the new
Creo que está apagado del...
El suyo.
¿Vale? ¿Tu continúo?
El suyo está, no está apagado el volumen del ordenador. Es que cargarlo.
¿Ahora? Do you hear me? I can hear you. Hello?
Hello.
¿Ahora?
Ahora sí.
Vale.
Well, Máximo, thank you for the presentation. Thank you for the nice presentation. Just a quick question. Do you have an estimate of how well the new model, the new resolution model, can resolve the cascade of energy compared with a 2 kilometer model?
Thank you. Because it's the glider facility from Sophie, a great collaborator. So, for the case of energy spectrum, this is the cascade of energy. So, this is the range of mesoscale and submesoscale. So, the 2,000-meter simulation don't solve well the submesoscale structure. The García-Jove law are the semi-quasi-geographic theories law. So here the new grid, the 650-meter horizontal resolution, solve the small structure, the submesoscale structure. This is evidence that the new grid is the good tool to reproduce the submesoscale activity in the Balearic Sea. And this is the cascade of the energy. So we have the transfer from the mean or the mesoscale structure to the submesoscale structure, and vice versa. It's more complicated. You think like you have a mesoscale ADB and you split in small long cavities and generate a submesoscale structure. Okay, because
yep.
Lilia,
go.
Hi, everybody, and glad to join to this seminar in Emilia. I have a quick question, focus on the physics that you are discussing, Máximo. In the beginning, you were saying that the Western Alboran geofront, was explained with frontogenesis processes. And if I understood correctly, in this gyre, you found the largest vertical velocities. Is that correct? And if this is the case, you could say that usually frontogenesis is related to strong vertical velocities always?
No. The quick explanation.
Okay.
The Western Alboran geofront is intensified, is stronger because they have the strong influence that they are affected from Lisa or two in 2018, something like that. They explain the frontogenesis is strong associated with the Atlantic jet, and this is a strong jet, and so this strong jet generated a stronger condition for the intensification of the vertical velocity. So it's for that in the Balearic Sea we have a similar, we have same frontogenesis mechanism to amplify the vertical velocity, but the vertical velocity is about 20-30 meters per day. It's the wind and the Atlantic jet is stronger than the others.
Okay, thank you.
No more questions? No? Okay, thank you, Máximo.